Okay. So, lesson 18, environmental chemistry. It's chapter 28 in your textbook, lesson 18 for us. The first question that we need to ask is this: what reactions happen in the atmosphere? What reactions happen in the atmosphere? Now, as you can probably imagine, I really like this question. You can probably imagine that because I wrote it, and I thought it deserved to be on a slide and be part of our discussion. But the reason I really like this question is because it reminds us that there is important chemistry happening with regards to living organisms here on Earth that is happening way above and beyond the realm in which we live. Okay, some of these reactions are happening literally tens of thousands, if not hundreds of thousands of feet above Earth's surface, and yet they have a huge impact on life on Earth. And it's just a good reminder that environmental chemistry is not just happening in the soil. Okay, environmental chemistry is happening everywhere on Earth, and they're really important reactions that are taking place. Now, another reason I really like this question is because it says what reactions happen in the atmosphere. And I will show you two reactions that are taking place, but the two reactions overall combine to do one thing. Okay? So we're asking a question of what reactions happen in the atmosphere, but really, we're really asking what is going on in the atmosphere to make life possible on Earth. And it's two reactions, one overall process. The first reaction: UV radiation separates oxygen into two atoms of oxygen. So UV radiation separates oxygen gas, or you might say molecular oxygen, into two atoms of oxygen. And so, in order to understand this, or maybe in order to appreciate this, we need to work a little bit with oxygen. So go ahead and draw this out. We've got our oxygen here. And what we're going to do is we're going to come up with the Lewis dot structure for oxygen, and we're going to anticipate or predict the way an individual oxygen atom is going to behave. All right? So if you have your periodic table, take it out. Open it up and find oxygen. And I need somebody to tell me the electron configuration for oxygen.
1s2.
1s2.
2s2.
2s2.
2p4.
2p4. Okay, so here we have the electron configuration for oxygen. That electron configuration gives us a lot of information. It tells us that we have 6 total electrons. Yes? Actually, 8 total electrons. I said 6 because I didn't write the 2 there. I messed my own self up. My own self? I messed myself up. My own self. That doesn't sound right. So it's this electron configuration tells us that oxygen has 8 total electrons. It also tells us that oxygen has electrons in 2 different energy levels. The first energy level as well as the second energy level. And it gives us some more information because we know that when we're trying to determine how an atom is going to react, the most important thing is the number of valence electrons it has. And we know that the valence electrons are all of the electrons in the highest energy level. And so if you look at the electron configuration for oxygen, what is its highest energy level? Energy level number 2. And how many electrons are there? 6. So this tells us that every oxygen atom, unless it's an ion, every oxygen atom that is uncharged has 6 valence electrons. How many does an atom want? 8. So it has 6. It wants 8. It tells us it's got a dilemma. And the best way to solve that dilemma is to gain 2 more. Okay? And there are several ways in which we can gain, but let's go ahead and draw the Lewis dot structure. So what we did in the past and what we will continue to do is we will put the two s electrons up on top. And the reason why we draw those first is because we know that as we're putting electrons around the nucleus of an atom, the electrons have to fill the lowest energy levels first. And 2s, this orbital, is at a lower energy level than the orbitals in the 2p subshell. Now, how many orbitals are in the 2p subshell? 3, right? Because that subshell can hold a total of 6 electrons. I don't know why I keep saying this because this is 7. It's 6 electrons. And every orbital holds 2, and 6 total electrons divided by 2 electrons in each orbital tells us that there are 3 orbitals. But we put these all together because they are the same energy level. So now we have a second rule that we have to bring into our work. The first rule is you fill lowest energy levels first. The second rule is leave electrons unpaired as long as possible. Okay? Well, here we have 3 orbitals that are all the same energy level. So there is not a lower energy 2p. They're all the same. Okay? So now we have to put 4 electrons in here, and we're going to fill them, basically, we're going to fill the orbitals in such a way that we leave the electrons unpaired as long as possible. Okay? So here we'll put 1 of our 4 electrons. Put it into, I don't know, let's call this 2px. Then we'll put a second one into what we'll call, I don't know, 2py. And then we'll put a third one into what we'll call 2pz. But we have 1 more electron. We have only accounted for 3 of our 4 2p electrons. And so now we have an issue where we have to start pairing our electrons, which is fine, because the only way to avoid that would be to start putting them into 3s, but that's at a higher energy level. And that rule wins out over the keep them unpaired as long as possible. Okay? So then we'll put our 4th electron, and let's just put it here. It really doesn't matter where we put it. They're all the same energy level. But we'll put it there. And now we have accounted for how many electrons?
6.
1, 2, 3, 4, 5, 6. And how many valence electrons does oxygen have again?
6.
1, 2, 3, 4, 5, 6. Okay? Now, we can see the problem that oxygen has, right? It's not just a matter of numbers anymore, where we're like, it wants 8. Well, my finger numbers make no sense. It wants 8. It has 6. It needs 2 more, right? But now we can visualize the problem. We have a half-filled orbital here. We have a half-filled orbital here. Wow, here. Orbitals do not want to be half-filled. That is unstable. That creates something that's very reactive. These half-filled orbitals are very reactive. Have you heard of oxidative stress? Have you heard of antioxidants? Okay? And so people tell you it's good and it's healthy to have antioxidants. You know what antioxidants do? They take these oxygen radicals that are super duper reactive and they neutralize them. Okay? Because if they don't, you know what these do? They go and react with everything. And sometimes they'll react with your DNA and they'll mutate it. That's not good. Okay? Would you agree that mutating your DNA, which is the blueprint for how you make proteins in your cell, is not good? It's not good. This is very reactive. Okay? And so oxygen like this does not stay like this very long. And it basically has 2 big options. Right? 2 main options. 1, take some electrons away from something wanting to give them away. Right? That's one option. The second option is to do what? Share electrons with something else that has a half-filled orbital, right? Here's oxygen, here's another oxygen, and guess what its Lewis dot structure looks like? Just like this one, because they're both oxygen. The only way it would be different is if it were an oxygen ion. Okay, and so now we have another oxygen atom that, look, it has 2 half-filled orbitals. You've got 2 oxygen atoms that are both very reactive because they have 2 half-filled orbitals. What about if we did this? Pair these up, and now instead of 2 half-filled orbitals, we combine those into 1 filled orbital. And what if we did this? Took these two half-filled orbitals and we combined them into one filled orbital. We'd have something that looks like this. We'd form what we call a covalent bond. We'd actually form two of them. Every covalent bond represents a now fully filled orbital that was formed by two half-filled orbitals. That's what every covalent bond represents. Every covalent bond represents a fully filled orbital that used to be two half-filled orbitals. These two orbitals combined. These two orbitals combined into a single full orbital. These two orbitals combined into a single full orbital. So every bond represents two electrons, and we've got two of them. And so now we have something that is very stable. How many electrons does this oxygen atom have around it? 8. 1, 2, 3, 4, 6, 8. Right? Because every bond is now a fully filled orbital. And there are two bonds. That's two fully filled orbitals. Each orbital has how many electrons if fully filled? 2. 2 times 2 is 4. 4 more is 8. This oxygen has 8. This oxygen has 8. Both are satisfied. And this is a very unreactive molecule. It's a molecule that life depends on. Okay? At least for what we would call obligate aerobes, which are organisms that need oxygen, which is almost all organisms on Earth. There are some organisms that are called anaerobes, and they can function in the absence of oxygen, but most organisms cannot. Josh?
So one oxygen by itself is very dangerous for you?
Very reactive unless it's this.
So it can be very dangerous for you, but if you get a couple of them together, then they're not dangerous anymore because they neutralize each other?
Yes, absolutely. Yep.
So an antioxidant could be oxygen itself?
Yeah.
But you'd have to get the oxygen to the other oxygen without a reaction.
Well, and the antioxidant would be more reactive oxygen, right? Which, yeah, you've got a delivery issue, right? So you've got to concentrate enough of this toxin to where it neutralizes itself, and hope that your numbers are right. Or you can just use something that will neutralize it and is not toxic itself. Okay, does this make sense? Okay, so this first reaction, all of this to just show us our first reaction. UV radiation separates molecular oxygen into two atoms of O2, or two atoms of oxygen. Okay, and so our first reaction is this. Right now we've got O2, this molecule of oxygen. We've got UV radiation. Where does UV radiation come from? Sunlight, UV radiation, and we get this. Okay, that's our first reaction. Okay, we take something that's very stable, UV radiation hits it, and creates two very reactive atoms of oxygen. Okay, that's our first reaction. Now, the second reaction. These free oxygen atoms that are very reactive will combine with other molecules of oxygen, with O2, to form O3, which is called ozone. So this is reaction 1. I'll give you a moment to write this, and then we'll write down reaction 2. Here is reaction 2. We've got this highly reactive oxygen atom. this highly reactive oxygen atom combining with this molecular oxygen.
No.
To form this. Where every oxygen atom in this molecule of ozone has a bond with the other two oxygen atoms. Okay. And this is a fairly stable molecule. But we'll talk a little bit more about ozone in a little bit. And these are our two reactions. Reaction 1, reaction 2.
The term ozone makes a lot more sense now.
Uh-huh. Yeah, now that you know what it is and what it looks like.
It's a bunch of O's.
Yep, absolutely. It's O3. Now, ozone, what do we know about ozone? It is deadly, but that's something we'll talk about in just a moment. It is deadly to interact with ozone, but remember, what reactions happen in the atmosphere? This reaction's happening way above the surface of the Earth. Okay? And in the atmosphere and in the high, what's the term I'm looking for? Strata, those layers of the atmosphere, ozone is necessary. Because what does ozone do?
It blocks UV radiation.
Yeah, it absorbs UV radiation. Makes it to where the sun can still heat the earth, and a lot of sunlight can penetrate for photosynthesis to begin the process of fueling life. But a lot of the most harmful portions of that UV spectrum are absorbed by ozone.
Very coincidental.
Very coincidental.
That's
Because
what-
UV light is the exact thing that induces the formation of ozone, which then filters out a lot of the UV light, so it doesn't hit our surface. Because if it did, DNA would mutate much more quickly than it does, and life would be very difficult. Life would be very difficult. One, to sustain life, and then two, to keep it working generation after generation after generation. All right, make sense? Okay, so there are two reactions, one overall process, and that's to produce ozone. So what reactions happen in the atmosphere? This is how you should answer it. The formation of ozone. What reactions happen in the atmosphere? The formation of ozone. The formation of ozone. Because you'll read that, and the question says reactions, and you're like, all I did was said one thing, but then you'll remember that it's a two-part reaction to get that one overall product. All right? Only key term I'd like for you to look up is ozone. Ozone.
It's kind of weird that the one oxygen atom is bad for you. 3 oxygen atoms
Bad for you.
So
Two,
two
essential for life.
essential.
Yep. Isn't it beautiful? It's like chemistry matters. Yeah.
And very coincidentally, on the Earth, we don't have much single or triple.
You don't have enough. You don't have enough of the right UV light to actually split oxygen atoms and create ozone at our surface, because the ozone made up in the Earth's atmosphere is filtering out enough of the UV light to prevent the formation of ozone at our surface. Beautiful. Well balanced. All right, what does burning fossil fuels produce? So a big part of environmental chemistry is focusing on fossil fuels. What are fossil fuels? What happens when we burn them? And what is the chemistry involved? And what are some of the implications? So this is the next question we're going to deal with. And I didn't put these down on the slide, but you all probably know if I said that there are 2 big negative things about burning fossil fuels, you could probably come up with those 2 negative things. Any thoughts? So greenhouse gas production. So one of that's going to be like CO2 production, greenhouse gas production, and what's the other one? Micah.
It's gonna run out.
Okay. It's going to run out. The other one is pollution. Okay, so the two big things that you oftentimes hear associated with burning fossil fuels are greenhouse gases, so creating gases that are going to trap heat, which there's really no arguing that, right? If some gases reflect sunlight back and are going to trap heat. And then the other one is pollution, and there's really no arguing that. But so then what we need to do is figure out, okay, well, what is actually happening scientifically, and not to have this discussion be so politically charged, right? Let's leave it like, okay, what's happening chemically, and then we can deal with that in kind of the second part. So what does burning fossil fuels produce? One of those things is going to be greenhouse gases, and I'll show you some of that right now. So big picture, burning fossil fuels forces oxygen and nitrogen to react. Burning fossil fuels forces oxygen and nitrogen to react. You probably know the answer to this question. You may not, but you probably do. I'm going to ask it anyways, even though I think it's just a probably and not a guarantee. What are the two main components of air? Oxygen and nitrogen. Oxygen and nitrogen together make up greater than 90% of the air you breathe. Even in a place like Southern California, where a lot of the air you breathe is smog and carbon dioxide, oxygen and nitrogen still make up well over 90% of it. Now, both of these are very stable. This oxygen is very stable. The reason why we need this oxygen, this is beyond what you need to know for this course, but the reason we need this oxygen is because it acts as a final electron acceptor when we're trying to generate energy. And so when it accepts some additional electrons, it forms water. But anyways, so this is a very stable molecule. This is a very stable molecule. They do not typically react. But they do when you generate enormous amounts of energy burning something, okay? Which is what happens when we burn fossil fuels, okay? And so we get oxygen and nitrogen reacting to form two molecules of nitrogen monoxide, which is one of our nitrous oxide molecules. Now, you're like, okay, well, what does this actually mean? This is highly reactive. This nitrous oxide is highly reactive and pretty much immediately reacts with more oxygen. So these two nitrous oxide molecules react with more oxygen to produce two molecules of nitrogen dioxide, another nitrous oxide. And you're like, okay, so this was reactive. It reacted with oxygen in the air to produce this, but you're like, what's the big deal? Now this happens to be fairly stable, but it's depleted some of the oxygen out of the air, which, I mean, that's unfortunate, right? We lost some of the oxygen to make this, and then we lost more of it to make this, right? And we kind of rely on oxygen. Yeah, Josh.
Probably just like Chalmers, can't see it well, but there's the 2NO
plus
2O, and you get 2NO2. So
yeah.
Is there, or what happens?
Yeah, are you asking about its balance?
So that's 4 O's right there.
Yeah, it's 4 O's because there are two here, two more here, 4 here.
And then 2 and 2.
Yep.
Two
Yep.
twos. Okay.
2 nitrogen here, 2 nitrogen there.
Okay, so the 2 under there kind of gets multiplied by that 2, or
Yes.
after the 2.
Yes.
Okay.
Yep. Yes. Yep. Absolutely. So the number in front gets multiplied to any subscript to
Right.
give you total number of atoms.
Good.
Yeah.
I couldn't remember that. We learned it before, but I couldn't remember.
Yeah,
that.
no, I understand. No, it was a good opportunity to ask that question. Okay, so here's the really big deal. UV light, even the UV light that moves through the ozone layer is enough to split these molecules of O2 or of NO2 into NO and single atoms of oxygen. Oh, sorry, I need to write on top of this arrow, and you should write on top of this arrow as well, UV light. Which again comes from sunlight. A lot of it got filtered out by the ozone in the upper stretches of the atmosphere, but some of it doesn't, and the amount that penetrates is enough to split this nitrous oxide back into something that we know is reactive, and two molecules of individual oxygen atoms. And what do these do? These oxygen atoms. They go and react with oxygen to form ozone. You see that mentioned here? The oxygen atoms go and react with oxygen molecules to form ozone. That's something that happens high up in the atmosphere to filter out UV light. Now we're making ozone where? Where are we burning fossil fuels? Are we burning them way up in the atmosphere? No, we're burning them at Earth's surface, right? We are burning them in your car, unless you have a fully electric car, right? You're burning fossil fuels in your car. You're burning them in power plants. Okay? And so we're burning them right at Earth's surface, which means now we're generating ozone where? Right at Earth's surface. And Ethan, you mentioned this earlier. Ozone is dangerous when it's low in the atmosphere. It's toxic. Ozone is a toxic material. It's a toxic molecule. Okay? Yeah, Joe.
Is there an exact definition of toxic? Because you hear it just thrown around with everything. This is toxic, and generally this means bad for you.
Yeah, I'm sure there is an exact definition. The basic meaning of that is that it's pathology inducing. So the pathology is when your body does not function the way it is supposed to. And so a toxic material will induce pathology. It'll induce your body to behave in ways that it is not supposed to. And that's why you can have things that are toxic for some organisms but not for others. Like a good example of this, I bought my son this very morning some pistachios because he loves them, and he's not doing super well. He's got some severe allergies to all the pollen that's out and about. And so his is more than just like respiratory issues. He's got hives all over his body, and his lips swelled up today. His eyes are swelling, and it's all to this pollen that's around. So I was like, I'll buy him some pistachios. He loves pistachios, but pistachios are toxic to dogs, and it's because in dogs, that meaning toxic, it induces pathology, it gets their body to function in ways that it shouldn't. They are not toxic to humans. Okay. And then you'll see things on like markers like non-toxic. What that means is it's non-toxic to humans. It doesn't induce pathology in humans. It doesn't mean that it's non-toxic to everything. Because again, that meaning toxic is induced pathology. Okay? So there's another reaction. This is fun. It looks like I wrote 20, but that's 2 oxygen. Yeah, Ethan.
Why doesn't the remaining oxygen just become regular oxygen?
Yeah, it's a good question. It can, and sometimes it will. But there's a lot more molecular oxygen surrounding it than there is free oxygen atoms. So it's a lot more likely that it's going to run into this before it runs into another free oxygen atom. Yeah, it's a good question. It's a saturation issue. Yeah. Josh.
So almost if you could contain the stuff that's coming off the burning, it could all come together.
That's our next question. Save that for a moment. There's another reaction I didn't put on the slide, but I want to show you another thing that can happen with this. So another possibility with this NO2 is to have it react with water. The reason I didn't put it on the slide is because we live in a dry place. There's not very much water in our air. But in some places, surprisingly enough, there is a lot of water in the air. They're humid, you know? Have you been to a humid place? Yeah.
I've lived in
You've lived in a humid place? Where did you live?
Puerto Rico.
Puerto Rico. Yep, that is a humid place. We should talk about this. I love Puerto Rico.
Oh, okay.
Anyways, that's another conversation for another time though. So another reaction that can happen is this nitrous oxide can react with water to form this. Let me get this balanced. So now that's 2, 4, 5, 6. Oh no, that won't work. Oh, I'm not going to struggle to get this balanced. Sorry. We'll just write this, and you can write under it, it's unbalanced. It's going to take me a while to balance it, and I'm not going to do it right now. Okay, but this right here is a strong acid. And what do strong acids do?
Get rid of all of their.
They dissociate, and it lowers the pH. And it's not great, because where are we making this? Way up in the atmosphere? No, we're making this at Earth's surface. And where's there water in the air sometimes in some places where you live? There's water right at Earth's surface, right? Where you have water evaporating off of bodies of water, off of people. And so now you're making an acid in the air right at Earth's surface. That's great, right? No, it's not great. That's not great. So that's another reaction. And then another one, burning fossil fuels produces SO2, sulfur dioxide. Burning fossil fuels also produces SO2, sulfur dioxide. This will react with oxygen and ozone and/or ozone to form SO3. So burning fossil fuels also produces sulfur dioxide, which will react with oxygen or ozone to form sulfur trioxide. And you're like, what's the big deal? What's the big deal? Sorry, I'll let you write that. I get so excited, I just keep talking. Bless you. This will also react with water, just like nitrous oxide will. Nitrogen dioxide will react with water to form nitric acid. SO3 will react with water to form sulfuric acid, which is another strong acid. And what do strong acids do? They dissociate, lowering pH. And we have another acid being formed where? Way up in the atmosphere?
Right here.
At Earth's surface, where we're burning the fossil fuels. Have you heard of acid rain? So this sulfuric acid, notice when this water, the best place for this is for this gas to react with the water as it's condensing in a cloud. And then now you form sulfuric acid that falls as rain. Okay? Which does a lot of really not so great things, as you can probably imagine. Okay, so what does burning fossil fuels produce? The way we'll answer this question is we'll just call it generally pollution. Generally pollution. What does burning fossil fuels produce? Pollution. And there's nothing really politically charged about that statement. It's chemical. Okay? That burning fossil fuels is absolutely going to produce pollutants. Now it's a question of how do we mitigate that? And this is what you were coming at, right? You're like, well, can we just remove some of these things? Let's talk. Okay, no key terms for here. How do we reduce the impact of burning fossil fuels? How do we reduce the impact of burning fossil fuels? Simply put, we use devices that are called catalytic converters. Catalytic converters. We use catalytic converters. Cars have catalytic converters. Big coal burning power plants have catalytic converters. And here's what catalytic converters do. They convert NO and NO2, are two different types of nitrous oxide, back into nitrogen and oxygen, the kind that you find abundant in the atmosphere. They convert these nitrous oxides into NO2. Okay, and so which means if we can do that, we can eliminate the production of nitric acid. We can eliminate the production of ozone at our surface. Catalytic converters will also convert carbon monoxide into carbon dioxide. We'll convert carbon monoxide, which is toxic, into carbon dioxide, which is not toxic. And we just discussed what the meaning of toxic is. And what is the meaning of toxic?
It
Induces pathology. Okay? And so it takes something that is toxic to something that is non-toxic, at least in normal numbers. Carbon dioxide is non-toxic in normal numbers. If you have too much carbon dioxide that you're breathing in, it does become toxic and will induce pathology. And so using catalytic converters reduces the probability of nitric acid production, so we've eliminated some of our pollution. Catalytic converters can also, now really good catalytic converters can pull sulfur dioxide out of the air as well. And so we've limited our amount of pollution production, and then overall the use of catalytic converters will also reduce the total number of greenhouse gases. Reduce the total number of greenhouse gases, those gases that trap heat. Okay, and so now the two biggest things that you hear associated with burning fossil fuels, they're both reduced with the use of catalytic converters. Right? Have you ever seen this written on the back of a vehicle? Have you ever seen this written on the back of a vehicle? This is zero emissions vehicle. It works for vehicles that are fully electric. This is partial zero emissions vehicle. This is for a vehicle that does such a good job reducing the production of nitrous oxide and sulfur dioxide that they have a rating that allows them to basically advertise themselves as a partial zero emissions vehicle. Okay? But ultimately, this is why we put catalytic converters on cars. And this is why we put catalytic converters on coal burning plants, wherever you're burning fossil fuels. All right? So how do we reduce the impact of burning fossil fuels? See first point. There's really no better way to answer it than that. We use catalytic converters. The last question we need to deal with is one that directly relates to the production of greenhouse gases. Is the global temperature increasing? This is something that's going to naturally come up when you talk about greenhouse gas production. If greenhouse gases trap heat, are we trapping more heat? Simple answer to this question is yes. Yes, global temperature is increasing. Yes, global temperature is increasing. Okay? Doesn't really matter where you go to find those data, you're going to find support for that. That global temperature is increasing. Here's where it gets, so chemically speaking, yes. But here's where something we really need to take into account, which very few people that talk about greenhouse gases will talk about. If the Earth is old, if the Earth is billions of years old, the rate of increase is unprecedented. If the Earth is truly billions of years old, then the rate of increase is unprecedented. This is the only side you usually hear when you hear about greenhouse gases, especially in the political spectrum. But the problem is, I don't think the Earth is old. And if the Earth is young, the Earth is still rebounding from a global flood and from the ice age that followed shortly afterwards. Okay? If the Earth is young, the Earth is still rebounding from the global flood and the ice age that followed shortly after. Make sense? And this last point, because the Bible very clearly teaches that the earth is young, right? If you read Genesis 1 through 11 as being a historical account of Earth's history, which I think for very many reasons you should, it flows very naturally that the earth is young. So the Bible teaches that the earth is young, and so when we take the rate at which global temperature is increasing, it is consistent with what you would predict. And is consistent basically from the last ice age until now, that the rate of increase has been basically the same. So the temperature is increasing, but the rate of increase has been pretty constant since the ice age. Micah.
So I know that we have proof that there was the global flood, it's in the
Yep.
Bible and everything. How do we know that there was an ice age that followed?
That's a good question. We have a lot of evidence for what's called glaciation, where you basically, as you start to, if the earth cools, ocean water is going to move at the poles is going to freeze. And so that ice shield that you have at the poles is going to expand. And as it does, it's going to expand. If it's from the North Pole, it's going to expand southward. From the South Pole, it's going to expand northward. Okay? And as it does that, the ice is going to carve rock out. Okay, as it expands. And then as it melts, as you start to warm from an ice age, it'll melt, and as it does, it'll start to release some of that debris that it's holding inside of it from carving out that rock. We have a lot of evidence of this in North America and in Europe, where the only way to really explain the way the soil is composed is that glaciers expanded, carved out rock as they did, and then they retreated as they melted and left that debris behind. Okay, so we have a lot of evidence of what we call glaciation. You also have a lot of evidence in the way certain lakes and rivers are built, and a lot of valleys. So a river, when it cuts a valley, if water cuts a valley, it cuts it in a V shape, like the Grand Canyon. Although the Grand Canyon is a very steep V, but it was water. It is a water-produced valley. Glaciers produce a U-shaped valley. And so we can find these in North America and in Europe, where we believe that the glaciers had moved through and carved out a valley, and you can see these U-shaped valleys. And then on top of that, the way some bodies of water are produced, you get, so glacial lakes are interesting. You know, typically a lake is just a place where water pools in a river. You know, a river's flowing and then water will pool somewhere in a lake. Glacial lakes aren't connected to any rivers. You just have a random lake in the middle of nowhere, or at least not connected to any rivers. And the reason, and then when you study the topography of the lake, the shape of it, it's like the tip of an iceberg. And so what happened was that pieces broke off of these glaciers and then basically went and, you know, pushed into the sediment and left like a, you know, a cone-shaped depression when that glacier melted, and then it filled with water.
So where do we have these lakes?
All over Michigan, all over Minnesota, some in Montana and northern Washington state, and then some in the eastern U.S., New York, Pennsylvania, some of those more northern states. Yeah, and then over Europe as well, but I'm not as familiar with European geology. Yeah, Joe.
Everyone's concerned about, you know, the warmth of the Earth getting warmer. Is it actually is it actually bad for us for the Earth to get warmer anyway?
Well, it's going to change. It's going to change environments, right? And so if global temperature is increasing, then some of your species that aren't as tolerant to warmer temperatures aren't going to survive. And you can even see that even over the last, you know, several hundred years, which we can trace back, and even sometimes a couple thousand years, and we can trace back. We've seen some plants and animals have to retreat to where you only find them now at high elevation, where they used to be more widely distributed when you had a cooler climate. But as things have warmed, they're basically restricted just to high elevations. So the big concern is that you'd lose some of the biodiversity on Earth that can't adjust fast enough. But the reality is, if what the Bible teaches about origins is true, and there was a global flood, which I believe it is true, we're rebounding from that flood, and the reality is, like, you're going to lose some of that biodiversity. Now that doesn't mean that, you know, we should deliberately make aspects of God's creation disappear, because I think that's a poor stewardship of what God has made. But there are some things that it's just, yeah, I mean, it's going to happen. So that's the big concern, is that you're going to lose some of the biodiversity. What does it mean for us? Some of the ideas are that climate will become more unpredictable, and more like natural disasters will happen more often. And when the air temperatures increase, so do ocean temperatures. And then so coral reefs are very sensitive to that, to ocean temperatures increasing. And so there's a lot of idea there too that we might lose a lot of the biodiversity in coral reefs, which something like 20 or 30% of Earth's population, human population, relies almost exclusively on coral reefs for all of their materials. So those are the big concerns. Yeah. All right. Well, gentlemen, that's it for today.